Ever feel like the universe is playing a giant cosmic joke on us? Like reality itself is just one big gotcha moment waiting to happen. Well, buckle up, because today's deep dive is taking us straight into the mind-bending world of quantum mechanics.
And trust me, the more you learn about quantum mechanics, the more you realize just how little you actually know. But hey, that's part of the fun, right? Luckily, we've got a great guide to help us navigate this wild territory, Jim Al-Khalili's book, Cuantica, guia de perplejos.
Which, for those of us who don't speak Spanish, translates to.
Quantum, a guide for the perplexed. Because let's be honest, even physicists who've dedicated their lives to this stuff are still scratching their heads over some of it.
It's true. Sometimes it feels less like a science and more like, well, magic.
And that's the thing about quantum mechanics. It challenges everything we thought we knew about how the world works. The rules of the game that apply in our everyday lives completely go out the window when you zoom in to the level of atoms and photons. The universe, it seems, plays by a different set of rules down there.
It's almost like we're talking about two completely different universes. I mean, on one hand, quantum mechanics is the backbone of so much of our modern technology. Computers, lasers, smartphones, none of that would be possible without it. But on the other hand, it's full of these paradoxes that make you question, like, the very fabric of reality.
It's not so much that the theories themselves are that strange. It's more that nature itself behaves in these really bizarre ways at the smallest scales.
Case in point, the double-slit experiment. So in our source, Al-Khalili talks about this experiment with these things called fullerenes. They're these tiny carbon molecules shaped like soccer balls.
But like a million times smaller than a millimeter.
Exactly. So even these relatively large molecules, at least compared to, say, an electron, even these guys act like they can be in two places at once.
It's not just being in two places at once. It's more like they travel like waves, spreading out and interfering with themselves. Like, imagine throwing a baseball and it suddenly decides to act like ripples in a pond. Our classical intuition just breaks down.
It's enough to make your head spin. And as Al-Khalili says, there's no rational way to explain it.
The best we can do is describe what we see. And what we see is that at the quantum level, the universe doesn't care about our neat categories of particles and waves. It just does its own thing.
And that thing didn't just appear out of thin air, did it? It wasn't like one day some physicist just shouted, "Eureka!" and boom, quantum mechanics was born.
Right. It wasn't some single eureka moment. It was more of a slow burn, like a bunch of little mysteries that physicists were trying to piece together back in the late 19th and early 20th centuries.
So they were kind of like detectives searching for clues.
Exactly. And the clues were these weird phenomena they couldn't explain, like black body radiation, basically, how objects glow when they're heated up.
And the photoelectric effect. That's where you shine light on a metal and it starts spitting out electrons.
Exactly. And these were just two of the big ones. So you've got all these brilliant minds wrestling with these puzzles. And eventually they start realizing that the answers point to a whole new understanding of how energy and matter work at the most fundamental level.
So it's like they were putting together a jigsaw puzzle, but the picture on the puzzle turned out to be something totally unexpected.
Exactly. And a key piece of that puzzle came from Max Planck. He was studying black body radiation and realized that, get this, energy isn't this smooth, continuous flow like we always thought. It's actually chunked up into these tiny, discrete packets.
And he called these packets quanta.
Right. And then a few years later, along comes Einstein, and he says, hey, maybe light itself is made up of these quanta, these little packets of energy.
And we now call those packets photons.
Exactly. And suddenly the world got a whole lot weirder. Because now you have light acting like both a wave and a particle.
Which makes absolutely no sense if you try to apply our everyday intuition to it.
And if that's not enough to make your brain hurt, just wait till we start talking about probability in quantum mechanics. Because it's not like flipping a coin, where if you knew everything about the coin in the flip, you could predict the outcome with 100% certainty.
Right. In the quantum world, it's like the coin is flipping itself even when no one's looking.
Exactly. Quantum probability is a whole different animal. It's not about our lack of information about the system. It's that the universe itself is inherently uncertain at that level. The best we can do is calculate probabilities.
So we can figure out the odds of finding an electron in a certain region of space.
But we can never know for sure where it actually is until we look.
Which kind of makes you wonder, what's going on with that electron when we're not looking? Al-Khalili uses this great analogy in the book. He compares it to a thief hiding out in a city.
Right. We might not know where the thief is at any given moment, but we assume they're in one specific place. But with an electron, it's like it's spread out over the entire city until we try to find it, and then boom, it's like it suddenly collapses into a single location.
It's like the act of observing forces the electron to choose, okay, now I'm going to be here.
And that, my friend, is one of the biggest mysteries in quantum mechanics, what they call wave function collapse. The act of measurement seems to fundamentally change the nature of the thing we're measuring.
Which leads us to, of course, the most famous thought experiment in all of physics, Schrodinger's cat. I feel like everyone's heard of Schrodinger's cat, but I'll be honest, I'm still not entirely sure I understand it.
The important thing to remember is that no actual cats were harmed in the making of this thought experiment. It's really just a way to illustrate the weirdness of this whole wave function collapse idea. So you've got a cat in a box, right? And inside the box, you've also got this device that's linked to a random quantum event.
Like the decay of a radioactive atom.
Exactly. And here's where it gets really strange. Until we open the box and actually look inside, the cat is said to be in a superposition of states, meaning it's both alive and dead at the same time.
Which is obviously completely impossible.
Right.
I mean, a cat can't be both alive and dead.
And that's the whole point. The thought experiment isn't really about cats. It's about highlighting how absurd it is to apply these quantum rules to our everyday macroscopic world. And it forces us to confront the very real possibility that our classical intuition, the way we think the world works based on our everyday experiences, might be completely wrong.
So, let me get this straight. We've got particles acting like waves, probability baked into the very fabric of reality, and a cat that's both dead and alive. My brain is officially fried.
And we're just getting started. Just wait until we get to non-locality, then things get really wild.
Okay, so you're telling me it gets even weirder than a cat that's both alive and dead. I don't know if my brain can handle much more weirdness, but all right, lay it on me. What is this non-locality thing all about?
Imagine 2 dice. You roll them, and every single time they land on the same number. But here's the kicker. One die is here on Earth, and the other is all the way out on Pluto.
Okay, now that's just messing with me. How could 2 dice, separated by billions of miles, possibly be connected like that?
Well, that's the thing about the quantum world sometimes. It really does feel like magic. This is the mind-blowing phenomenon known as quantum entanglement. It's like these particles have an invisible thread connecting them no matter how far apart they are.
So are you saying if I measure the state of one entangled particle here on Earth, I instantly know the state of its entangled partner, even if it's out by Pluto?
You got it. It's like information is traveling between them instantaneously.
But wait a minute, wouldn't that mean things are moving faster than the speed of light? And didn't Einstein say that was impossible?
You're right. This isn't just about breaking the rules. It's about rewriting the rule book entirely. Quantum entanglement throws everything we thought we knew about cause and effect right out the window.
So we've got particles acting like waves, probability woven into the fabric of the universe, a cat that's both dead and alive, and now particles that are linked across billions of miles. I'm starting to think the universe is just showing off at this point.
And we haven't even gotten to quantum tunneling yet. Remember that analogy we talked about earlier with the ball mysteriously appearing on the other side of the hill?
Oh, right, you mentioned that. It sounds kind of like, well, cheating.
It might sound impossible, but in the quantum realm, it's just another day at the office. This is quantum tunneling in a nutshell. Particles can essentially tunnel through energy barriers that, according to classical physics, they shouldn't be able to overcome.
So in a way, quantum tunneling is kind of like finding a shortcut through reality.
That's a great way to put it. And it's a good thing, too, because without quantum tunneling, stars like our sun wouldn't be able to burn.
Wow. I never realized how important quantum tunneling is for, the existence of everything. So it's not just theoretical, it has real-world implications.
Absolutely. It's not just about stars and the universe at large. Quantum tunneling plays a vital role right here on Earth. For instance, without it, we wouldn't have transistors, those tiny little devices that power our computers and smartphones.
Okay, so we've gone from particles acting like waves to particles literally tunneling through walls. I'm almost afraid to ask, but what other kind of quantum weirdness is out there?
Well, for one thing, these bizarre quantum phenomena aren't just confined to the lab. Researchers are finding that quantum mechanics plays a role in biology as well.
Quantum mechanics and biology. Now, that's a curveball I wasn't expecting. I thought we were talking about electrons and photons, not living cells in DNA.
It's a relatively new area of research, but it's pretty mind-blowing stuff.
Yeah.
For example, there's evidence that quantum phenomena, like the tunneling and entanglement we've been talking about, might actually be essential for processes like photosynthesis.
Hold on. You're telling me that plants might be using quantum mechanics to make food from sunlight?
It's looking more and more likely, and it's not just plants. There's a theory that birds might actually use quantum entanglement to navigate during migration.
Birds using quantum mechanics to navigate. Okay, now that just sounds like something out of a superhero movie. How could birds possibly be doing quantum physics in their little bird brains?
It's all about a special type of molecule they have in their eyes called cryptochromes. These cryptochromes are sensitive to Earth's magnetic field, and scientists think that they might be using quantum entanglement to sense those magnetic fields and figure out their direction.
So birds are basically flying around with tiny quantum compasses in their heads. That's incredible. Okay, I need a minute to let that sink in. Let's shift gears for a bit and talk about something a little less mind-blowing, like maybe the future of technology.
Sounds good.
So we've talked about how quantum mechanics is already responsible for so much of our current technology. But what about the next big thing? What about quantum computers? I feel like I hear about quantum computers everywhere, but I'll be honest, I'm not entirely sure what they actually do.
It's not just about making our current computers faster. It's about harnessing the bizarre rules of the quantum world to perform calculations in ways that are fundamentally different from how classical computers work.
So how is that different from just, making our current computers faster? What makes quantum computers so special?
Imagine you've got a maze, and your job is to find the way out. A classical computer would try every single path, one at a time, until it stumbles upon the exit. But a quantum computer, it could, in a way, explore every single path simultaneously.
Wait, so it's like having a superpower that lets you be in multiple places at once.
That's a great analogy. You see, quantum computers use these things called qubits. And unlike a bit in a classical computer, which can only be a 0 or a 1, a qubit can be in what's called a superposition, meaning it can be a 0, a 1, or both at the same time.
Okay, that's starting to sound a lot like our cat that's both alive and dead. So by using these qubits, quantum computers can explore many possibilities all at once.
Exactly. And by entangling these qubits together, we can create these massive computational spaces that would take a classical computer billions of years to even begin to explore.
Okay, so we're talking about solving problems that are basically impossible for even the most powerful computers we have today. What kind of problems are we talking about?
All sorts. Think designing life-saving drugs, creating entirely new materials, breaking the encryption that protects our online data, and revolutionizing the field of artificial intelligence.
It sounds like quantum computers have the potential to completely change the world as we know it. But like any new technology, I imagine there are challenges in actually building and using these quantum computers.
Absolutely. One of the biggest challenges is something called decoherence. You see, qubits are extremely fragile. Even the tiniest disturbance from their environment can cause errors in the computation.
So it's not like we'll all have quantum computers in our homes anytime soon.
Not quite. But we're making progress every day. And while widespread quantum computing might be a few years off, the research being done right now is paving the way for some really groundbreaking technological advancements in the future.
It's an exciting time to be alive. But there's one more quantum thing I have to ask you about before we wrap up. What about teleportation? Is it really possible to teleport things like they do in Star Trek?
Well, I hate to break it to you, but beaming people up or down is still firmly in the realm of science fiction.
Oh, man. So no teleporting myself to a beach in Fiji.
Not just yet. But what we can do is teleport information. It's called quantum teleportation.
Quantum teleportation. Okay, so how does that work? Do you need some kind of special transporter beam like in the movies?
It's even stranger than that. It all comes down to the power of entanglement. Remember how we talked about entangled particles being linked across vast distances?
Yeah, like those two dice, one on Earth and one on Pluto,
Yeah.
always landing on the same number.
Exactly. Now let's say we have two entangled particles, one here on Earth and one on Mars, and we want to teleport the information from a third particle here on Earth to the one on Mars.
So we've got our two entangled particles, one here, one on Mars, ready to beam down some information.
No transporter beams necessary. What we do is take the particle here on Earth, the one whose information we want to send, and let it interact with our Earth-bound half of that entangled pair.
Okay, so they're like swapping secrets or something.
Something like that. And at that precise moment, we make a measurement. Now, because of the uncertainty principle, this measurement doesn't reveal everything about our original particle, but it gives us a crucial piece of the puzzle.
I'm sensing a but coming.
But, and this is the really mind-blowing part, that measurement we made, it instantly affects the state of the entangled particle on Mars.
Instantly, even though they're millions of miles apart.
Millions of miles, different planets, as if there's an invisible thread connecting them.
Yeah.
That's the magic of entanglement.
So what happens next? Do we just, email the Martians and tell them what we saw?
Not quite email. We do still need to send information the old-fashioned way, at the speed of light or slower. We transmit the results of our measurement, maybe using radio waves, fiber optic cables, whatever works.
So it's like sending instructions along with this instantaneous tangled link.
Exactly. On Mars, they receive those instructions, and because they've got the other half of our entangled pair, they can use that combined knowledge to reconstruct the information from our original particle.
So it's not like we're physically moving the particle, more like we're transmitting its blueprint and recreating it on the other end.
And perfect way to put it. We're not beaming people up just yet, but this technology is still in its early stages. Who knows what the future holds?
Imagine unhackable communications, or a quantum internet where data travels at warp speed. This has been one serious mind-expanding deep dive, from particles behaving like waves to cats in superposition, entanglement, tunneling. It's enough to make you question everything you thought you knew about reality.
And that's the beauty of science, isn't it? Always pushing the boundaries of what we think is possible. We've only scratched the surface of quantum mechanics, and who knows what other incredible discoveries await us. Maybe some of our listeners will be the ones making those breakthroughs.
And if they do, we'll be sure to have them on the show. Thanks for joining us on this journey into the weird and wonderful world of quantum mechanics. Until next time, keep asking questions and stay curious.